So I put my pretty little diagram now. Again, this was the universal mapping problem for the direct product. Here we have this family of modules AI, and for every one of these modules, there's a homomorphism, say phi sub k from C into AK. Of course, we've also got projection from the direct product. And so it's not just this, but also these projections onto the factors. Given this situation, there's a unique homomorphism C into the direct product, such that this diagram commutes. This symbol just means that going this way is the same as going this way. That is to say, dk is equal to the capital Phi and pi k for all k in the index set. All right. And the direct sum was the same sort of animal in the sense that you started with a possibly infinite collection of modules AI, and this time you have the homomorphisms from the component modules out to D. Right. You also have the inclusions into the direct sum. This gives a homomorphism unique such that when I do I over k, and then I do capital pitchfork, I get baby pitchfork for all k in the index set. So these are kind of dual properties, right? They're kind of mirror images of each other. And both the direct product and the direct sum are uniquely determined up to our module homomorphism by this property. So if you have some other mystery module here that satisfies this, right? So you've got these inclusions and you've got this family out here, then there's this, then it has to be isomorphic. So I'm going to prove this for direct product, and I'm going to leave the direct sum proof. It's almost, it's almost the same, except probably in one place with the arrows sort of turned around. I'll leave that as an exercise. Proof of, I guess it's 632. This is the direct product. Okay, so the first thing I want to do is let's just get down and dirty and let's define phi. I need a phi from C into the direct product of AI. Okay. My goodness, what is there to do? Okay, so input, something in C. Output needs to be a generalized sequence, one of these nets. With each component in AI. Oh, how am I going to do this? Look, for every C, this homomorphism is going to give me an appropriate thing over here, right? So why don't I just fill this up with again, this is math, so we're not going to do it if it ain't easy. Let me point out how this works. Note. I'm going to be careful here and show you this normal homomorphism. What is this? This thing is right, just by definition. But each of these little animals are our module homomorphisms. So within this parenthesis, I can split this up, right? So this is phi C1 plus R phi C2 Great. And I can split this up again because the way we add things in the direct product. Which is so indeed it's normodular homomorphism. And let's check this out. If I look at capital Phi and then pi k, let's just do C. Well, this is pi k because that's what capital Phi does to this. Right? And what is this? Well, this means, hey babe, just read the kth coordinate, right? So what do we have? So the diagram continues. And actually, we've essentially proved that this is the only way to do it, right? Let me try to render this more explicit. This guy is another R-modular homomorphism. That is to say that pi k then essentially we go through the same sort of exercise that we already went through and to see that this is exactly what we need. So notice that this is a homomorphism that goes from C into the direct product. I don't know much, but this has to be. If it's going into the direct product, it's got to be a net. And so what are these coordinates? Well, this thing determines exactly what the coordinates are. If you look at pi k, this is pi k of ci, which is ck. But by the same token, this has to equal pk of C. And so these functions give exactly the same output. Everybody okay so far? Nothing really surprising, right? I mean, I love this theorem, right? Because it sounds all fancy, lots of words, and makes me feel really intellectually superior or something. But the proof is very, very easy, really. I mean, it's almost like following your nose. And here's like the real meat of it. I really like this. It's the fact that this is here's the universal part. This last, maybe sort of at this point, cryptic statement made about, well, okay, this thing is unique up to R-modular homomorphism. So let's kind of go through that. Suppose that product suppose D is another solution. So in other words, what we have is we have D, and for every one of these AKs, there is a homomorphism here. And there's this right here. So this is not maybe projections, whatever the analog projection here is. And these maps here, then there exists a unique B such that, let me call this alpha K, such that B, well, okay. So assume that we have another solution, right? And our burden is we want to show that this D, this other one that solves this problem with perhaps different projections, actually is isomorphic to our direct product. So I'm going to turn the triangle around a little bit. So we have the diagram. We have C2. And we get this on here. But this should work. So let's equal D, right, itself. And what do we have here? Well, we have D. Can somebody give me an obvious solution to this mapping or homomorphism here that will work? Right, so we have the maps from D to AK, they're whatever these new ones are. Use these same maps here, and this is the solution, and it should be the only solution, right? So let's store that up for a bit. We're going to use that in a moment. Now let's consider this diagram. I'm going to draw it this way. AK. Now, and consider this diagram here. Now, D is also a solution. Well, AK is a solution to this. We have these maps from D to AK, right? So this gives me a map here. I'll call it that. Right. And why does this work? This works because we proved this about the direct product, right? That is, there has to be this map that goes from C into the direct product. In this case, C is being played here, and here's the direct product. But see, D also is a direct product, right? In the sense that it solves problems. We have this map here, and we have maps from D into AK, same one here. But if D satisfies that mapping problem, then there has to be a map from here. This is now playing the role of C, right? So there has to be one here. If I agree. Compose F and G. And now we've got our triangle here. So what does FG have to be? By the uniqueness of this right here, so what do we have so far? Well, we're almost there because we know what this is the composition of two functions. This means F has to be 1 to 1 and G has to be onto, right? But I don't know either F or G is an isomorphism yet. But how do I get around that? Now, D and the direct product decide to spice up their love life, a little role playing. They do some role reversal here. And that's exactly what we're going to do. Now D plays the role of the solution to the mapping problem first. And so this gives this here. So notice that when you do F and G, this is the identity on the direct product of AI. And so yeah, yes. So in particular, D is isomorphic to the direct product of AI. I mean, whenever I do this proof, it almost feels like I need to take a shower. I feel a little dirty, like I've gotten away with something. But this is really kind of a cool thing, right? The uniqueness, which was easy to show, the uniqueness of this map was easy to show, and it gives a really nice consequence that the direct product is the only solution. There's very similar proof for the direct sum, and I encourage you to try to work through that as well. Okay, any questions? You know, probably when I first saw it, I always thought that direct product was kind of the daddy max. But we will see that with a lot of the theorems that we're going to do, the direct sum, well, at first blush, direct sum is probably a little bit more useful. And we'll see a key theorem on that later. Not that direct product is not, it certainly is. But let us first, I'm going to dig a little bit deeper into the notion of direct sum here. It's direct sums, one of the good things, especially computation. Direct sums are kind of cool to deal with, especially if you've got a finite direct sum. A lot of number theory and cryptography do this kind of thing. You look at coordinates and the computation is correctly simplified. So if I walk up to you on the street and I give you a module, it might be of interest to say, hey, this module you gave me, can I decompose it into a direct sum of some of the submodules? And the following theorem tells us when we can do that. Proposition. Let R be a ring, and we have family R submodules And let's see, a family are submodules of some parent module. Show you something I'll pay. Let's suppose a couple of things. Number one, A is the sum of family AI. That is to say, let me give you a couple words of caution about this notation I'm using. Remember what this means is this means a sum of elements that can each be taken out of AI. But remember the sum is zero almost everywhere, right? So this is only a finite sum, even though I go index over what could be uncounted many modules, only finitely many of the things that I use for a given element, but there's only finitely many non-zero ones, right? But let me make this less confusing, perhaps. Another way to put this when I say A is the sum of the family of those modules is if you get a shovel and shovel all those modules into a big bucket, they will generate A, right? So that's basically it. Those modules as a set generate all of A, right? And here's the directness in the sum. 2. Let's say for all K in the index set, AK intersect AK bar is 0. And here, I'm gonna have to say what I mean by AK bar. AK bar is the sum of AI so this is what is generated by all the AIs that are not AK, right? So this is kind of a strong condition because what it says is if I select any of these AIs out, and then I see what's generated by the rest of the modules, there's only 0 and no. Right? But if you have these two things, then A is isomorphic, the direct sum of AI. So that's the condition that you need right here. And this one certainly merits. Oh, any questions so far on the setup there? Okay, here's what I'm going to do. I'm just going to go for broke on this proof, and I'm just going to set up a function. We're going to find P from the direct sum of AI into A. Now, here's the tricky part, perhaps. So my input is this sequence or even bigger, maybe a net of stuff, right? It's like this long list of ordinals. I need to take that string and I need to get something in A. How can I do this? I see. Yeah.
Would it work to just add the elements?
Like this. What are you, some kind of crazy analyst? Right? that looks like an infinite sum. Well, it looks like potentially an infinite sum to me. But he's right. Well, why am I not worried about the fact that that's it?
Because, we know there's only a finite number of non-zero.
Exactly. This is right here, I think, in this part of the proof, we see the importance of direct sum. It allows us to do this. And that's why, because the first time I ever saw direct sum, it's like, okay, you're making crap up now. Why are you letting almost everything be zero? Well, this is why, because it allows us to get this homomorphism into A, right? Recall that AI equals zero almost everywhere. So this is truly is a finite sum. D is an Armand homomorphism. I'm just gonna make that statement, but it's easy to check, isn't it, right? Because when you add two things like that, you just get a bigger sum. It's still a finite sum. Everybody comfortable with that? Okay, so this is an Armand homomorphism. What do we gotta do? We gotta show that it's one-to-one and non-to. Can somebody explain why it is on to? That's essentially right. Condition one. So this is disguised to say this guarantees that the homomorphism is going to be onto. Let A be an A, then all I have to do, notice that A assumption A is a finite sum, AI1 plus AI2 plus AIT with I sub j an index set. Right? And so let's say xi be defined by xi is equal to 0 if I is not equal to I1, I2 up to IT. So this is 0 everywhere that doesn't have one of these, and AIJ if I is equal to IJ. And notice that B of xi equals AI1 plus AIT, which is A. So it's on to it. The more delicate part is the one with oneness. Any questions? One to oneness. Let's suppose AI the internal function. Well, of course, remember, this thing only has, we'll say that AI1, AI2, these are the possible non-zero entries. That's fine. Actually, let me take another step here so that I structure this. I'm gonna get a complication. Suppose Okay, so suppose that this element of the kernel is not zero, that means it's got to contain some non-zero entries, and there's only finite many of them, because it's a direct sum. Notice that phi of sequence AI, the net, is AI1, AI2, AIT. Right? And of course, these elements are all non-zero. Anybody see? Anybody know what the rock's picking? Let me do the indentation. This means AI2 plus AI3. So AIT is equal to minus AI1. Agreed? Now, where does this live? This is certainly in AI1 because that's where that lives. Where else does it live? Lives in, yeah, I'll just do it that way. Because this is in the sum of AI2, AI3, AIT. So it's in the sum of AI1, AI2, AI3. So certainly it's in the sum of everything this is. What's the intersection of this? The intersection of this is zero. Therefore, AI1 is equal to zero, which is a contradiction. So, whatever I call it, phi is also 1. And that establishes the proposition. Okay. Any questions? Okay, so now that we've talked about direct sum, and of course this, I really like this proof because it illustrates why the direct sum itself might be important. And we'll see more of that later. But first, I want to talk about how many of you, just out of curiosity, how many of y'all heard of exact sequence before? Where does it come up? Does it come up in algebra? Does it come up in number theory topology? Right, this is very important. Exact sequences are one of the places where the rubber meets the road for the meaning of algebra and topology, right, for example. But it's really weird because when you look at the definition, this is another one that's like, okay, there was somebody with way too much time on their hands making this crap up. But it turns out that it's got lots and lots of really cool applications. And in fact, exact sequences are an algebraic object, which I'm going to define for you in a moment. But this purely algebraic object can be used to measure, for example, how many holes you have in a manifold, things of this nature, right? Which is really cool when you get that kind of connection. Definition 6.1. I'm going to expand on this a little bit. A sequence of R module homomorphisms and I'm going to index it this way. It's called, oh, let me put these maps names. So there's 2. Is called a complex. And this one would actually be, I always get this confused. I think it's a chain complex if your indices are decreasing, co-chain if it's increasing. I've never really cared that much about the distinction. But we're going to call this a complex if so that is, we call this a complex if whenever you compose 2 of these functions in a row, you get the 0 on the things, right? That's all that means. So this means, let me point out, let me give kind of another interpretation of this before I move on with my definition. This means the image of Fn is contained in kernel of the next map, right? That is to say, image Fn is contained in kernel of Fn. That's essentially what it means for those 2 things to compose to 0. Now, somebody came along and said, gee, I wonder what would happen if this were an equality, right? And it's actually amazing. It's amazing to me. There's many applications in topology, for example, and other things, even things in factorization that I've done, where very naturally you come up with chains of maps where 2 in a row compose to 0. There's lots of natural applications where this comes up. And then you take the second question, and that is, what if you have equality? What if it's not the case that, well, I mean, what if it's not only the case that the image of Fn is contained in kernel measurement? What if you have equality? And like I said, in topology, the failure of this, that is, this measures things in dimension, say, n, about various geometric. So that's kind of a cool application we'll look for later. Moving on with the definition, we say the sequence is exact at an if the image of Fn is equal to something Fn plus 1. So complex means this everywhere. Exact at an means that you get an equality. So it's a special type of complex at that point. You get equality of image of Fn is equal to kernel of Fn plus 1. We say sequence is exact if it is exact at an for all n, for all relevant. Okay. Any questions? Let me give you a definition. And this definition might make you worried. I'm going to freak out and go all kinds of crazy stuff, but worry not. There's a reason for this. An exact sequence of the form 0 A B C 0 is called a short exact sequence. let me make a note here. So this is kind of, good first thing to notice. Okay, suppose I walk up to you on the street and I give this 0, A, B, C, 0. I say it's the exact same. What can you say about F? It has to be 1-to-1 because the image of this map is 0, right? And it should equal the kernel of this map. Well, if the kernel F is 0, that means F is 1-to-1. What does it mean by G? It's surjective because the kernel of this map is clearly all of C. Everything goes to 0, and that has to be the image of this map. So G is onto. And of course, you get exactness in the middle. So a short exact sequence is kind of nice because the first non-trivial map is 1-to-1. The last non-trivial map is onto. You get exactness in the middle. The first thing that you might wonder is, why do they call this a short exact sequence? It certainly looks like I could make them shorter. Oh, sometimes I will call this an SES, short exact sequence. What's true about this exact sequence? What's true about F? Well, because of the exactness here, F is 1-to-1, right? Because the image of this is 0, it's kernel of this. And the image of this has to be the kernel of this, but the kernel of this is all of B. So what is true about F? It's an isomorphism, right? We call this a BES, for boring exact sequence, which is why nobody ever pays attention to it. You just say, look, A and B are isomorphic, and that's it. So short exact sequence, the reason they call it is this is as short as it can be and still be interesting. There's also something else, and this will be a homework problem coming up. It turns out that if I walk up to you on the street and I give you any exact sequence, even infinitely long, this is another good reason for this to be a short exact sequence. If I give you any exact sequence, you can obtain this from short exact sequences. That is, you can take a whole bunch of small short exact sequences and weave it into a long, even an infinitely long exact sequence, and vice versa. You can tear apart it down into short exact sequence. So in a certain sense, if this is a molecule, that's an atom. Does that bring back any bad memories for you? So, okay, any questions so far? Okay, so sometimes we write things in this form. Give some examples here. Sometimes people, especially people like homological algebra stuff, uh, or I'll just say this, a sequence of the form is exact if and only if F is 1-to-1. Right? A sequence of form BC0 is exact if and only if G is onto A sequence of this form is exact if and only if F is an isomorphism, as we've seen. Let's look at some more interesting examples here. How about this? Uh, okay, let's look at this sequence of C module homomorphism. So I'll make it easy. Where okay. So this first map is just multiplication by n. And the second map, y, is y bar. That is just reduce that mod in. Maybe I should write it that way. Would everybody agree that the first map is 1-to-1? Right? Because if nx equals 0, then, well, let's not take a 0 map, right? Now, I think we would have to agree that that Fn is 1-to-1. It's also true that phi n is onto, isn't it? Right, because it's only finite, and then cosets mod n, and you can just cover that from 1 through n, right? And let's look here in the middle, the image of Fn is equal to precisely nz. Right, so the image of that is precisely all multiples of n, and this is precisely the kernel of pi n. So this is a short exact sequence. Okay. Here's kind of a big standard way to build an exact sequence. A good example of a short exact sequence, and I'm going to contrast that really quickly with the previous example. Same. Let C anyone you met, anyone you met. And I am going to find this map. I'm going to call this inclusion into A, and this is projection onto C. And the way the compositions work here is A goes to the order pair A0. And the way the second map works is the order pair AC just reads the last coordinate. Right? So notice clearly the first map is 1-to-1. And the second map is onto. And what is the image of this? It is everything in the form A0, which is precisely the kernel of the next map. So this is short. This is a short exact sequence. But, and this will be my Jerry Springer final thought for the day. There is a major difference between this one and in general. Does anybody know what it is? The maps here on the top one are invertible in a certain sense. You could run this sequence in reverse. C goes to 0C and AC projects to A. And notice when you do this map and compose it with this map, it's the identity on A, right? So if I go here to A0 and then I use this map to go back, it projects back to A. And if I do this map, it goes to 0C and project back, it goes to C, right? Can you do that here? Well, the easiest way to see that it can is how in the world are you going to map from Z and Z? Because even with groups, this first and foremost, there have to be a homomorphism with billion groups. Everything in here is a finite order. And everything here is an infinite order except for the identity. The way to go from here to here is 0. So you don't have much hope being able to reverse this. And we will talk about this distinction later. Any questions? Questions? All right, y'all have a good one, and we will see you on today.